Tell me a little bit more about this interplanetary internet. And what's the concept behind that?
So some of you will remember that in 1997, the Pathfinder robot landed on Mars. And it was the first successful landing in something like 20 years or so, because the previous landing of the Viking was 76. And so in 97, the Pathfinder arrives. And of course, we're all very excited about it. I was at the Jet Propulsion Lab with the team that worked on this. And we were looking at each other saying, boy, that was cool. And then we started thinking, gosh, all of our missions up until that time had used point-to-point radio links for control and for data retrieval. And we thought, boy, that seems so limiting. What if we had a network like the internet that worked all the way across the solar system? Then you could support manned and robotic space exploration far more readily than you can by just having these point-to-point dedicated links. So we, sitting around the table, said, okay, what if we wanted to build an interplanetary internet? What would that look like? So we started out thinking, well, we got TCP/IP and it works on Earth, so it ought to work on Mars. And then we started doing the math. It would work on Mars. The problem is the distances between the planets is big and variable. So just use Mars as an example. When we're closest together in our orbits, we're 35 million miles apart. So if you do the math, light is 186,000 miles a second, which is too slow. And it's at least 3.5 minutes to Mars and then 3.5 minutes back when we're closest together. When we're farthest apart, we're 235 million miles apart. That's 20 minutes one way, 40 minutes round trip. I can tell you that the TCP protocol was not designed with a 40-minute round trip time in mind. Flow control is very simple. You basically say, I'm running out of room, and the other guy says, okay, I'll stop sending until you tell me you got some more room left. Well, if it takes 20 minutes for the other guy to hear that you don't have any room left, the packets are still flowing for 20 minutes, and they're falling on the floor, and the dog eats them, or whatever happens. So that didn't work. Then we ran into this other problem. It's called celestial motion. The planets are rotating, and we don't know how to stop that. So if you're talking to something on the surface of the planet and the planet's rotating, eventually you can't talk to it anymore until it comes back around, just like a satellite. So we have variably delayed and disrupted communication in space. So we said, okay, new protocols. So we designed a new suite of protocols we call the bundle protocols, because that sort of sounds like packet. And they are delay and disruption tolerant. So we went through 4 iterations of that design from 1998 to 2004. Then the 2 rovers, Spirit and Opportunity, landed in January on Mars. And they were designed originally to transmit their data back to Earth on a point-to-point link to the Deep Space Network. These are 70-meter dishes in Canberra, Australia, in Madrid, Spain, and Goldstone, California, that were developed in 1964 to support our space program. So the rovers were supposed to transmit data back from the surface of Mars at 28.5 kilobits a second. And of course, the scientists were all grumpy about that. And then the radios overheated. And so we said, we don't want them to damage the equipment on the spacecraft, so we're going to back off on the duty cycle to keep them from damaging either themselves or the other instruments. Now the scientists are hopping mad. Then somebody else says, wait a minute, there's an X-band radio on the rovers. Yeah. And he says, well, there's also an X-band radio on the orbiters that had been sent ahead of time to map the surface of Mars to figure out where the rover should go. But they'd finished their job, but they're up there in orbit. They have power, communications, and computing capability. We reprogrammed them and the rovers so the rovers would hang on to their data until an orbiter got overhead, and it would squirt the data up to the rover at 128 kilobits a second, because it wasn't very far away compared to going all the way back to Earth. So we get 4 times as much data rate. And then the orbiter would hang on to the data until it got to the right place in its orbit to transmit data back to the Deep Space Net, which it could do at 128 kilobits a second because it had bigger antennas and more solar power, and it was outside of the atmosphere on Mars. So we built a store and forward network using the prototype implementations of the interplanetary protocols. So all the data that's come back from Mars, from those rovers, including the Mars Science Laboratory, has come back through this store and forward network. Meanwhile, we've perfected the interplanetary protocols. We've standardized them with the Consultative Committee on Space Data Systems, which is a UN organization made up of all the spacefaring nations. So now that's standard. It's available as source code on GitHub. It is now running on the International Space Station. So now we have a two-planet and one International Space Station network that we can use to test the protocols. The plan now is that a deployment plan is now in development, so that all the spacecraft that NASA produces and the other spacefaring nations, if they wish, will carry these onboard protocols. Now, even if they don't use them for their primary mission, when they finish their primary scientific mission, they could be repurposed as nodes of an interplanetary backbone. And so as the missions are launched in the subsequent decades of the 21st century, we'll literally accrete an interplanetary backbone over time. So by the time 2050 or 2060 rolls around, we'll have a backbone network that we can rely on for both manned and robotic space exploration.
That sounds
What's not to like about that? I mean,